So in the last video, we learned about refraction, which is the apparent bending of light as a result of it changing a medium or changing speed. And a byproduct of refraction is total internal reflection. That's where it appears that light gets trapped inside of a material. And that's also due to refraction. The light gets in, but as it's trying to leave, it refracts, and it refracts so much that it stays within that material. And we're going to be learning about that today. So diamonds are a classic material that we will see total internal reflection. It appears that the light is being collected inside of the diamond and coming out at very sharp angles. And another material that allows us to have high-speed internet is fiber optics, which also uses glass or some type of high-dense material that keeps the light within the fiber, doesn't allow it to leave, and it's based on this principle of total internal reflection. So that effect usually only happens when light travels from a material with a very high refractive index to another material with low refractive index. And if you remember from the last video, materials with high refractive index have high density. So diamonds, which are very dense, have a very high refractive index. And the fiber that we use are glasses that are plastics that have very high refractive index as well. And that allows us to trap light inside. Okay, and we're going to try to figure out how that happens using Snell's law in the video below us. Okay, so here is a little schematic showing us how it happens. So the light is already inside of a material and it's trying to escape into the air. Okay, the refractive index of water in this case is 1.33 and the refractive index of air is 1.00. So remember, internal reflection happens when the light is going from a high refractive index to a low one. That's why the arrows are going this way. And if you did Snell's law, you applied this equation, okay, using these refractive indices, you would see that the light gets bent away from the normal line. That little dashed line is my normal line. Okay, so my refractive angle is going to be greater than the angle of incidence under this situation. So it starts to refract away. And then if I start to move that angle a little bit further away, that angle of incidence a little bit further away, and make that angle larger, and if I apply it to Snell's law, plug those values in, I would find out eventually I will get to an angle where my refracted angle is 90 degrees. Well, what does that mean? That means that the light is going to skim the surface of the water. It's never actually going to leave. And if I approach an angle even larger than that critical angle, just by 0.1 degrees, well, now that refractive angle is going to be even greater than 90 degrees. That means that nothing is going to escape, and that all that light that hits that surface is going to reflect, and I will have no refraction happening whatsoever. And that's what we see in this diagram over here. That angle is larger than what we call a critical angle, and we get total internal reflection. Okay, and that's what's happening in these materials. Okay, these materials have forced light to bounce around inside, okay, because they have very, very small critical angles, okay, that we have been determined using Snell's law. Okay, so just to recap, the internal reflection occurs when the refracted angle is 90 degrees or greater. Okay, and all materials, or depends on the two materials that are in contact, those two materials when put together would have a critical angle that defines the minimum, or like that maximum angle before light can't escape anymore. Okay, and that's our critical angle. All right, so let's do some analysis over here. Okay, so here's a little video showing water and air. Water has a refractive index of 1.33 and air has a refractive index of 1.0. Okay, and applying this relationship, all they did was move the angle 1 degree at a time and calculate the angle of refraction. And they would see that that angle of refraction eventually approaches 90 degrees, which means that 49 degrees angle of incidence is equal to my critical angle. That's where light is just skimming the surface. Any angle of incidence greater than 49 degrees is going to cause total internal reflection in between water and air. Okay? And so how we would calculate 49 degrees, let's just try to do that with Snell's law. Okay, so remember, theta 1 is the angle of incidence, theta 2 is my angle of refraction, n2 would be, in this case, air, that's the refractive index of the material where the light is being transferred to, and n1 is the refractive index of the material where the light is coming from. Okay, so if I rearrange this equation, All right, sine theta 1, my angle of incidence, times n1 divided by n2 is going to be equal to sine theta 2. And remember, when theta 2 is going to be 90 degrees, that's for my critical angle, what sine of 90 degrees is 1. All right, so I can rearrange that equation further and say that, under these circumstances, when that angle is 90 degrees, I have reached my critical angle. So sine theta 1 becomes theta critical, which is equal to n2 divided by n1. That's pretty simple. Okay, so in this case, all they had to do was plug in 1.00, which is the refractive index of air, divided by 1.3, and then do the inverse sign, and that got them a critical angle of, that's 49 degrees. Okay, we can see that there. So animation is very simple to calculate. All right, well, let's try a different material. Okay, like what would happen if I changed water to something that has a higher refractive index? So here's a sample problem where we're going to calculate the critical angle when light travels from crown glass, something that we'd use in like a fiber optic, to air. Okay, so in order to get that going, we would first have to write down some information that we know. The refractive index of air is 1.0. The refractive index of crown glass is 1.54. I got this from your textbook. Okay, then we draw a diagram, a ray diagram showing refraction. So here's N1 being glass, N2 being air. That's the material we're going into. This red ray is showing the light coming into that interface. This green hashed line is going to be my normal line. Okay, I'm just going to erase this other little line in there. Okay, that's my normal line. And that is my refracted ray. Okay, so when we're trying to think about the critical angle, that's the angle at which the refracted angle is 90 degrees. And anything beyond this angle is going to cause that internal reflection. So by applying this formula, that sine theta critical is equal to n2 over n1. n2 in this case is 1.00. n1 is going to be 1.54. So theta c is equal to sine, okay, which in this case is going to be 40.5 degrees or so. Yeah, 40.5 degrees. All right, so we can take a look here. If I raise the refractive index of the material that's below air, what did that do? That made the critical angle even smaller, which means that more light is going to be trapped inside of that material. The light would have to approach that interface at a very steep angle to leave. So anything beyond 40, which is a whole 50 degrees, all those rays that would be coming in, okay, so if I was a ray coming in this way, I wouldn't be able to get out. I'm just going to be reflected into the material. I'll be trapped in the material. So good fiber optic material would have a much steeper critical angle. Okay, now diamond, so the refractive index of diamond is 2.5. So you can imagine that diamond traps light even better because its refractive index is much, much greater. If I applied that into this formula, I would have a much smaller critical angle, which would explain why when we look at diamonds, we see light coming out in these vertical crevices, okay? You have to be looking straight on it, and that's why they shine like a brilliant diamond, all right? And that's it for total internal reflection.